In our previous video on fine-tuning an AI model, we looked at the connection between raw pixels and emotional intelligence. We learned how fine-tuning works by using the concept that a dog's face isn't an image. It's a pixel grid, which we transform into a high-dimensional matrix to analyze the sentiment. Welcome to CareerLink, your hub for building, learning, and applying AI in the real world. Today, we're gonna apply the same foundational concepts of AI fine-tuning and actually fine-tune an AI model to detect pet emotions only using visual images. We'll be focusing this video for technical entrepreneurs, students, and developers. Quality AI starts with quality data. We are using the dog emotion dataset from Kaggle. It's a balanced dataset with 4,000 images divided into 4 classes: angry, happy, relaxed, and sad. Such a balanced dataset prevents the model from developing a majority bias, where it simply guesses the most common emotion regardless of the input. We are working in the Antigravity IDE. Our first step is structural organization. Notice the directory. We have a dedicated datasets folder and a models folder for versioning our weights. We open labels.csv to ensure our metadata matches our directory structure. Without this ground truth, the loss function cannot calculate the error. We define our stack in requirements.txt file. We include Torch for tensor operations and Torch Vision for its specialized image kernels. We add TIMM, the PyTorch image models library, which gives us access to industry standard architectures like ResNet and EfficientNet. Finally, Matplotlib and Plotly are added for visualization. By running pip install, we install all the dependencies. In config.py, we define the hyperparameters, the settings we change to control the learning process. We set our image size to 224. Mathematically, resizing every image to a square matrix of 224 by 224 ensures that the input dimensions for our first convolutional layer are consistent. We also define our device here, checking if a CUDA-enabled GPU is available. If not, we default to the CPU, though training will be significantly slower. The batch size is set to 32. This means the model will look at 32 images at a time, calculate the average error, and then update its weights. We set the learning rate to 1e-4. This is the step size for our optimizer. If it's too large, the model might overstep the mathematical minimum of the loss function. If it's too small, the training will take forever to converge. In dataset.py, we build our pipeline. We use transforms. We start with random resized crop. By taking different crops of the dog's face, we are teaching the model translational invariance. Basically, a happy dog is still happy even if it's off-center. We then convert the images to tensors, changing the data format from a standard image file into a multi-dimensional array of floating point numbers. We also apply color jitter to vary the brightness and contrast. This prevents the model from being light sensitive We want to recognize emotions in a dark room or a bright park. Finally, we normalize using the ImageNet mean and standard deviation. This shifts our pixel values to a distribution with a mean of 0, which helps the mathematical gradients flow more smoothly through the deep layers of our network during backpropagation. In CNN model.py, we first define our dog emotion CNN from scratch. We build a sequence of convolutional 2D layers followed by ReLU activation and maxpool 2D. This is the classic LeNate style structure. We aren't using pre-trained weights yet. We want to see how much the model can learn purely from our 4000 images. We initialize the weights randomly, meaning at epoch 0, the model has no visual intelligence. Our custom layers use 3x3 filters to scan the images for edges and simple textures. Each convolutional layer is followed by a pooling layer, which reduces the spatial dimensions of the matrix while keeping the most important features. We flatten this data into a 1D vector and pass it through a linear layer to get our 4 emotion scores. It's a clean, simple architecture, but as we will see, it has its limits. In utils.py, we write our evaluation logic. Inside evaluate model, we use torch no-grad. This is vital. It tells the math engine to stop tracking gradients, which saves memory during validation. We calculate cross entropy loss to measure the distance between the model's guess and the actual label. This score tells us exactly how much the model needs to adjust its weights to improve its accuracy. I am starting in train.py, where we will manage our custom CNN model and configuration files. We define the train function, importing the Atom optimizer and setting up data loaders. By using our dedicated configuration file, we easily move the model to the GPU, set the cross-entropy loss, and prepare lists to track our metrics over time. In the training loop, we iterate through batches using TQDM for a visual progress bar. We follow the standard workflow, a forward pass, a loss calculation, and backpropagation to update weights while monitoring accuracy in real time. After training, we switch to evaluation mode to test the model against validation data. If we hit a new peak in accuracy, the script automatically triggers a save function to store the best performing model weights. Finally, we use Matplotlib to plot our loss and accuracy curves to analyze performance and check for overfitting. We launch train.py using our custom Scratch model. Watch the logs. The accuracy climbs quickly at first, moving from 25% to 40%, but then it hits a wall. Around epoch 30, the accuracy plateaus at approximately 50%. Mathematically, the model has learned basic shapes, but 4000 images isn't enough for it to understand complex semantic features like the tension in the dog's eyebrows or mouth. Despite our best efforts with data augmentation, the Scratch-built model simply can't break through the 50% barrier. It's essentially coin flipping between similar emotions like sad and relaxed. To fix this, we need a model that already understands the visual world. It's time to upgrade our architecture to a pre-trained ResNet 18 using the TIMM library. Now, this is where actual fine-tuning begins. We modify our model code to load a pre-trained ResNet 18. This model was trained on ImageNet, over 1 million images. It already knows how to see eyes, fur, and facial structures. We replace its final layer with our 4-class head. This is called transfer learning as well. We're taking a genius vision model and giving it a crash course in specifically identifying dog emotions. We start with a pre-trained ResNet 18 backbone, freezing its layers to focus on our custom classification head. In the training script, we use a 2-stage process. Phase 1 trains only the head for 10 epochs, adapting it to our dog emotion data without altering the backbone. In phase 2, we unfreeze all the layers and lower the learning rate using a reduce LR on PlayTube scheduler for fine-tuning. The script tracks loss and accuracy throughout, saving only the best performing model weights. With the model trained and saved, we are ready for predictions. We begin stage 1 of fine-tuning, training only the head. We freeze the ResNet backbone so its pre-existing knowledge isn't destroyed, while our new classifier learns the basics of our dog dataset. This keeps the training stable and ensures that we are only optimizing the final layer that maps visual features to emotional labels. What's the difference in the terminal? With the ResNet backbone, we blast past our old 50% limit almost immediately. The pre-trained features are doing the heavy lifting. By epoch 20 of this new run, our validation accuracy has already climbed to 72%. The model is now seeing semantic details that were invisible to our scratch-built version. Now for stage 2, full fine-tuning. We unfreeze the entire model. Every single weight in the ResNet 18 is now unlocked. This allows the deeper convolutional filters to make tiny, delicate adjustments to specifically fit the features of canine faces. This is how we move from a good model to an expert model. Because we have unfrozen the whole model, we must drop our learning rate significantly. We move from 1e-4 to 1e-5. This ensures that our updates are very small, preventing us from overwriting the valuable pre-trained knowledge. It's like using a fine brush for the final details of a painting rather than a large roller. As we approach the final epochs, the accuracy breaks through 80% and finally settles at 82%. This 32% jump over our scratch model is proof of the power of fine-tuning. The model has mathematically mastered the dataset. We are no longer coin flipping. The AI is making a high confidence, data-driven, emotional assessments. Training is complete. We save the final state dictionary as a path file. This file contains millions of optimized numbers representing our model's intelligence. We have successfully transitioned from a failing scratch model to a high-performance engine. It's time to see what this math looks like in a visual format. Let's analyze our results. Our loss curve shows a beautiful downward trajectory for both training and validation. The fact that the lines are close together means we haven't overfitted. The model isn't just memorizing pictures, it's learning generalized features that will walk on new, unseen type of dogs, as well as its variety of species. Similarly, our accuracy graph tells the story of our project. You can see the plateau of the custom model followed by the massive spike once we switched to ResNet 80. The final curve is stable at 82%, indicating that our stage 2 fine-tuning successfully squeezed every bit of performance out of our 4,000 total images. Now, let's make this usable for the real world. We use Streamlit to build our web application. We write the code for the dog emotion recognition engine. We want a clean interface where anyone can upload a photo and get an instant emotional analysis based on the math that we just calculated by training a model. In the background, the app must process every upload exactly like our training script did. We apply the 224 pixel resize and the normalization transforms. If the input data format is different from what the model learned, the predictions will be wrong. We are ensuring mathematical consistency between training and inference. The model outputs raw scores, which we pass through our softmax function to get probabilities. We use Plotly to create a live bar chart so users can see the model's confidence. For example, it might be 80% sure a dog is happy, but 10% sure it's just relaxed. This transparency is a hallmark of good AI design. First, live test. We upload a joyful husky. The engine processes the matrix and returns happy with 76.8% confidence. Look at the probability chart. It correctly identifies the open mouth and relaxed eye features. Our ResNet upgrade by fine-tuning is paying off with high precision detection, and we can clearly see that. Now for a high-intensity test. This dog is baring its teeth. The model returns angry with over 81% confidence. Because we unfroze the backbone in stage 2, the model is sensitive to these specific tension patterns in the muzzle and ears. It's the flawless identification of a really complex emotional state. Now it's time for the final test. The Basset Hound. These dogs are really tricky because their natural facial structure can look sad. However, our model, having seen 1,000 real-world sad examples, correctly flags this as sad with nearly 80% confidence. Our 82% accuracy model has truly captured the visual essence of canine emotion due to fine-tuning. So that's it. From a folder of images to an 82% accuracy engine, that is the real power of what fine-tuning can help us achieve. If you are ready to stop guessing and start building, subscribe to our YouTube channel as well. And also, make sure to visit us at CareerLink to join our specialized AI circles to build projects like this with a community of experts and builders. Future-proof your career with our platform. Until then, see you next time and goodbye.